Next, we will determine the transfer function for the optimum filter, as it is unknown to us till now. We will do it in such a way that it will maximize the ratio. We already know that probability of error for the optimum filter is 1 by 2 ERFC x01t minus x02t by 2 root 2 sigma. Now, if that ratio is maximized, then probability of error will be minimum because it is monotonically decreasing function. Here FC is a monotonically decreasing function. If that increases, ERFC this one will decrease. So as a result, we need to maximize the ratio. Now we can, this 2 root 2 is a constant, we cannot change it still, but we can manipulate the ratio x01t minus x02t by sigma. We can manipulate the ratio, and if we maximize this ratio by using some filter transfer function, then we can reduce the probability of error. So we'll assume this difference as x01t minus x02t as x0t by sigma. So our goal is to maximize the ratio. So we need to maximize the ratio x0t by sigma. The square of the ratio, see signal component by noise component, we can say square of the ratio as signal power by noise power, signal by noise, that is square of the ratio equals x0 square t by sigma square. It is equal to x0 square t, and sigma square is the variance, noise variance, and noise is given by n0t. Noise is n0t. So variance we calculate, variance is mean square value. So I need to take square of the noise, then I need to take the mean. So that will be noise variance. So we need to maximize the ratio. Let us assume that filter transfer function is HF. Filter transfer function is HF, which will give minimum signal to minimum the probability of error and maximize this ratio. So filter transfer function is HF. So we can write that HF, x, the Fourier transform of this may be x0 t, Fourier domain may be, we can write xo f, and we have maybe some xt, we have some filter that is HF, and output may be xot, it will be h small t. I'll rewrite this one. So in time domain, maybe you have xt, filter transfer function may be ht, and output is x0t. Actually this one is the output. And frequency domain, you can write xf, you have hf, xo f. So as a result, you can write xo f. So output in this time domain, output is convolution of input and impulse response, and frequency domain output xo f is multiplication of xf and hf. Thus you can write x0t, see here capital T, because we are taking the sample, it is minus infinite to infinite HF. So we are taking the inverse Fourier transform of this one. HF x of f e to the power j omega j 2 pi f. Now in this case, as we are taking the sample at the time t equal t, so we'll use capital T, not small t, df. Okay. Similarly, for noise we'll use the power spectral density. Now assume input power spectral density is SNIF, input PSD of noise, and output PSD SNOF is output PSD of noise, power spectral density. Now input and output power spectral densities are related by SNOF equals HF square SNIF. So that's how these two power spectral densities are related. And we know power can be achieved, output noise power P can be achieved by integrating the power spectral density minus infinite to plus infinite SNOF df. So that's how we can achieve the noise power or mean square power. So this component, this ratio x0 square t, we can achieve from this expression, and noise power is determined from this expression. So we have both the components. So n0 square t means mean square power equals minus infinite to infinite. So SNOF we already know. So we'll use these two expressions. So as a result, our signal to noise ratio S by N and output equals x0 square t by sigma square equals, so I'll take the square of the x0, so I'll take this square, so this square will be the absolute value square because it may be a complex number, so it will be minus infinite to infinite hf xf e to the power j omega j2 pi ft df divided by minus infinite to infinite hf square SNIF df. So we have this signal to noise ratio. So that was our expression, and to minimize this expression once again, we'll use Schwarz inequality, which tells that so the square of the absolute value, it can be less or equals to minus infinite to infinite theta 1 x square dx into minus infinite to infinite theta 2 x square dx. See here we have the expression square of the absolute value of this term, and we'll use Schwarz inequality in such a way so that we can eliminate this term. And we can express signal to noise ratio with simpler form. So here to eliminate this one, Here we shall consider that theta 1 f equals root over SNI f HF, and theta 2 f equals 1 by root over SNI f XF e to the power j 2 pi f t. So if we multiply theta 1 and theta 2, then we can get this term once again. This root over and 1 by root over will cancel each other, so remaining HF, XF and that part. So it will be similar to this one. Why we are doing this? We are going to eliminate the denominator term. Now if we replace this theta 1 and theta 2 in main expression, so S by n will be less or equals so this one is theta 2 actually, minus infinite to infinite theta 2 f df. Then we can minimize this as it should be less or equals So we have used Schwarz inequality and replace this absolute value square in terms of this form. As you can see, we can cancel out this one and this one. So minimized expression S by n O will be less or equals minus infinite to infinite theta 1 f square df, or we can write S by n O less or equals minus infinite to infinite theta 1 f. We already know that it is SNI f. So absolute value square will be this one into HF df. Sorry, I did mistake here. It should be theta 1, because theta 1 is this part. It should be theta 1. It should be theta 1, and remaining this part will be, that should be theta 2, and theta 2 absolute value square of theta 2, so it will be 1 by SNI. So that absolute value square will be 1 by SNI f. Then XF, absolute value square of XF, and absolute value of this one is 1, so this will be 1. So that will be the signal to noise ratio, or in compact form you can write S by n O less or equals minus infinite to infinite now maximum value possible when this equals this, that is the maximum signal to noise ratio. So signal to noise ratio, our goal is to maximize this signal to noise ratio. So S by N O max, so that is our goal. So that will be equals minus infinite to infinite xf square by SNIF df. Now this is only possible when theta 1 f equals k times conjugate of theta 2 f. So that is only possible. So this is inequality, that is that inequality will be equal, that will be the maximum value. It is only possible when theta 1 f and theta 2 f are related by this expression. Or you can write using theta 1 value and theta 2 value. If I replace this, theta 1 is root over SNIF, so that is maximum signal to noise ratio. So theta 1 f is Sn root over SNIF HF equals k times conjugate of theta 2, k times 1 by root over SNIF into x star f. The conjugate of this, it will be minus, it will be a minus j2 pi f t. From this you can find the transfer function hf. hf equals k times x star f by SNIF e to the power minus j2 pi f t. So that will be the transfer function for optimum filter, which will give a maximum signal to noise ratio and minimize the probability of error. Or in other words, you can write the signal to noise ratio